Welcome to Cryptography and Hardware, the 9th session. Here we move forward and we leave the alias or symmetric cryptography. And now today we see the hash functions, and particularly we concentrate on Keccak. What is the motivation for the hash functions? I mean, many of you have seen other lectures and you know in which situation you actually need digital signature. Yeah? Because two parties need to communicate with each other and they want to prove that they have done something or somebody else want to prove that, hey, you have done something, and then the solution for that was digital signature through the public key cryptography. Now, if you're not familiar with this, I mean, probably you need to look at RSA and also ECDSA signature schemes. Yeah? And this is the scheme which it works. I mean, based on the principle, you have two parties, and then one of them, for example, Bob, sends the public key to the alias or publicizes this public key somewhere, and then you have a message, and then based on the message you sign it using your private key, and then the signature is sent with respect to together with the X, and then the verifier here has the public key and also the X, the message, and also the signature, and can check whether the signature is valid or not. Of course, not having the private key of the signer, only the public key. And this is the main idea, that you can actually verify this, that somebody signed something. And then, of course, the signature must change for every document. And the signature is actually a realization of a function with a message X as input and also the private key. I mean, this is something that you already have seen in the previous slide. Now, the problems of using digital signature over the message is that the naive signing of the long messages generates actually a signature of the same length. I mean, if you have a long message, a file, which is, for example, 1 terabyte or 1 gigabyte, no? I mean, if you want to sign it, then you probably need to spend the same amount of area or space just for the signature. And then checking this is also pretty hard. Yeah? Another one, I mean, is the computational overhead, which I already explained, and the overhead of the message also explained, and there is also security limitation. What is a security limitation? These messages or packets are completely independent of each other, and they are signed individually. Means that here X1 and X2, if they are completely the same, the signature will be also the same. And then somebody can actually swap it with another one. No? Then if you know the message and you know the valid signature of that message, you can easily replace it with another packet. Then instead of signing the whole message, we need to sign a digest, which is called a hash. No? And it's the same and it's secure, similar to signatures. I mean, it means that after hashing, you do the signature, and the same security level is achieved or maintained, but it's much faster, because you do the hashing and then the signature is applied only on the hash. There are different constructions for the hash, but it's actually like this, usually, that you have X, which is given to a function, and then the function generates the hash, and then this hash is just part of the message because the hash function receives also a limited size of the message, and then the message is divided into parts, and then it's given again and again to this hash function, and finally the last hash is taken and then is signed, and this is something which is sent out. No? And usually the hash functions don't have any secret. I mean, this is just a function. This is again the protocol, which is already explained, that somebody hash and then also sign. Clear? And there are 3 security properties of a hash function, just as a recall, if you have seen it or you have not seen it. There is a pre-image resistance. Because usually X is larger than hash, then the question is whether you can gets some x which generates the same hash. You know? And now here the second pre-image resistance is connected also to this pre-image, yeah? But it means that, okay, finding exactly another x which generates the same hash. And collision resistance means with the second pre-image, x1 is given, and then for one particular hash, you want to find another message which generates the same hash. For collision resistance means that whether you are able to find two messages which can generate the same hash. You know? Good. There are different algorithms and different standards you probably have heard. And then there was a standardization process similar to the AES. For example, there was SHA-1, and it was 1993 or 1995, and then block size of 512 bits, and the result of the hash or digest was 160 bits. And then it has been shown that there are some attacks, for example, collision attacks possible on SHA-1, and then SHA-2 was introduced 2001 as with the block sizes of 512 and 1024 bits and different sizes for the digest. And some attacks have also been shown, you know, particularly pre-image and length extension attack. And then finally, in 2016, through a long procedure, again similar to the AES, one design called Keccak was selected as a SHA-3, or a particular instance of the Keccak was selected as SHA-3. And it supports many different block sizes and then also arbitrary digest size. We will review shortly how the SHA-1 works. I mean, to just give you an idea how these hash functions work. This is part of the MD4 family, and based on Merkel-Damgard construction, means that here you can see that, of course, you have to also consider that the size of the input of the hash function is fixed. And if the input is smaller than the size of the hash function or input of the hash function, then, or block size, you need to pad it. No? And there are different methodologies and structures and definitions for the padding. We don't deal with the padding at the moment. Suppose that if the message is smaller than the block size, now it's padded, and it goes to the compression function. At the first round, when you just give the first block of the message, then it H0, which usually, for example, is constant value, either is full zero or something else, is given here, and then it continues like this, rotates, and then it generates finally for the last block, it generates 160-bit digest now. Something is defined based on the maximum length, for example, and then compression function consists of 80 rounds, means that this compression function here, what you have, has 80 rounds. I mean, if you implement it even in hardware, even if it's a round-based implementation, means that you apply 1 round per clock cycle. Again, you need 80 clock cycles just for one compression function. And then of course, this 80 rounds, I mean, they're divided into 20 different rounds. You know, means that 4 parts and each part 20 rounds. And this is the padding, for example. I mean, just for your information, how the padding works. You know, just as a reference. That the message is there, then you pad it by this. The size L of the message will also show up in the padding, and the rest is here 1000. You know, which should be everything actually 512 bits. Then the computation of the hash was like this, that each message block xi, which you see it here, is processed in 4 stages with 20 rounds each. I mean, each of them has 20 rounds. And then it computes a 32-bit word, this message schedule, what you see here, you know, 32-bit words, with W0 till W79. and then uses 5 working registers of sizes 32 bits. I mean, it's just a definition. I mean, there is no register here. If you have a software implementation, you may consider that they are registers and each of them is 32-bit, but in hardware, you don't need to consider them as a register. You know, they are just 5 inputs, each of them 32 bits, and 5 outputs, each of them again 32 bits. And then these are different operations and of course different definitions for each of these stages. And what you see here, the symbol here is arithmetic addition. You know, they are added together, again, modulo 2 to the 32. You know, means that is everything, the output is 32-bit. If I'm not mistaken, yeah, it should be 32-bit. No? Then the output of this, as I said, is just one digest, but then if it's not the only message, then it needs to go up and it's used as the input again for this hashing. You know? This is the construction, which is actually what I explained is called Merkle and Damgard construction. You know? That actually the last hash is used as the input for the next computation of the digest. The internal structure, probably we don't need to spend much time on it, but everything is very well designed for hardware. You know? In hardware, you can easily do that. Everything is just Boolean operations and also this additions, you know? this modular additions, and they are just shift. The additions are very well and very optimized in software because you have in software just adder that you can use, but in hardware, you need to implement these adders. We will deal with these adders later, you know, how we implement them in hardware. You already learned something in digital technique, how to implement the adders and the problems of the adders and so on. But the adders play a crucial role in most of the, or some of the cryptographic implementations. You know? But then in software, this is easy, this part. This shifting might be also done, but bitwise operation might be a bit hard, you know, if you bitwise change something, yeah. But usually this implementation can be implemented in hardware and software. With the only problem in hardware is just these adders, which are actually after each other, yeah. Either you need to just have one adder and then reuse it, then instead of one round of this, you need 4 clock cycles, yeah, instead of 1 clock cycle. But in software, anyway, you have to spend a couple of clock cycles for each of these instructions. Now, SHA-2 was also, I mean, a structure of SHA-2 was very similar to SHA-1, I mean, with some changes and differences, but that was the same construction and these functions were different till the open call of NIST with respect to having a new hash function. And before that, Keccak was already defined and published, and then Keccak was actually selected. Now, the Keccak works completely differently. It's based on a sponge construction. It's not Merkle-Darmstadt construction, and I can explain it how it works. Now, there is a permutation function here, f. You know, there is a permutation function. We will review this, and it's defined based on the variant of the Keccak or hash function because it's a sponge construction anyway. And then you start, for example, with 0, 0. Completely, you have a register which is fully with 0. And then something which is called R, which is the rate of the sponge function or construction and the capacity of it. And then before applying the f, the permutation function, you have the message block, which is the size of the R, means that you divide the message into the blocks of R bits. And then the first one is applied here, XORed, and then the permutation function is applied over the entire state. Means that if the size of this is R plus C, the output of the F is also R plus C. And then, I mean, this F also doesn't need to be invertible, you know? It doesn't matter. And then the next part of the message is XORed till the messages are completely done and all of them are XORed. And then you have the last permutation function and it's called absorbing, you know, up to here. And afterwards, you take part of, again, this construction, which is again R bit, or you are allowed to take r bit as part of the hash or digest. Then how long do you want it? I mean, you take z0, which is r bit, you need more, then you apply again f, you take another r bit, and so on. Of course, it's defined by Keccak, the bond, how many bits you're allowed to take. You know, I mean, you are not able to take as long as you want. But this is something which is defined based on the criteria of symmetric cryptography up to how many bits you are allowed to take from this. Okay. There is a link for the standard. Yeah, we will review now how the Keccak is built. There is a link for the standard in FIPS. You can have a look, which is FIPS 202. And this f function is pretty easy to implement in hardware. I mean, easy not, I mean, you will see, but it's efficient. It consists of only XORs and some AND gates. You know? Mostly XORs because of the diffusion function, and then the XORs just to keep the nonlinearity. Now, this is the sponge construction, which I already explained. You know? Then there is also a padding, and it's also defined, but should be the padding. But it doesn't matter, it's exactly as I said. But the size of this, the state of the construction is called B, which is the sum of R plus C, rate plus the capacity. And then there are different sizes or instantiation of the sponge function. It's called permutation Keccak F, and there are 7 different versions with B equals 25, which is almost a toy example, or toy version, up to 1600. Yeah? Means that the size of this, again, B was size of this, yeah? The entire size of the input and the output. And then security, speed of trade-off there are, but you know, most of or all of the SHA-3 candidates, they use the B equals 1600. The largest B is used for all of the instances of the SHA-3 because there are different SHA-3 standards. There is not only one based on the security that you want, based on the size of the hash that you want, and so on. Then there is a lightweight instance, you know, which is also 200, B equals 200. As I said, B equals 25 is kind of a toy version, but B equals 200 already provides some level of security, which is similar as SHA-1. Now, I mean, even if you use Keccak with this version with rate 40 and capacity of 160, then you still have a level of security, although the size or state of the permutation is just 200 bits. How it's seen, the state is seen by 5 by 5 bits. You know, this is 5 bits by 5 bits. And here you have as many as parts which are required to fill the B. You know, what was the B? For example, 25. Then 5 by 5 is just this one. You know, and then it's just one state. You know? Then the state will be just 5 by 5. If you have, for example, 1600, yeah, then you have 5 by 5, 25. Then you divide 1600 by 25, and then you know how many of this plates you need to have have the full state of the permutation. And it's actually called slice. You know, it means that each of them is called a slice. It's a 5 by 5 bit or 25 bit slice. Now there are different names. You see here there is something which is called a lane from here. Means that they have the same position in different slices, but here this is a lane. Here is a slice, which I already explained. Here is a row, and here's a column. And now we get into the functions, different functions inside the permutation function, or Keccak F. The first one which we deal with is the chi function. The chi function is the only nonlinear part or the only part which has some nonlinear gates. You see that the implementation can be written very simply. There are some AND gates, and one of the inputs is inverted, and then XORed with another input, and then it's now shifted or rotated, and it comes here. Yeah. Then 5-bit to 5-bit means that actually on every row of every state this can be applied. Yeah. The algebraic degree of this is 2, means that you just have just AND gate, and the inverse of it has the algebraic degree of 3. This might be not very important for you, but from symmetric cryptography perspective or protection against side channel attacks is pretty important. This is also officially written by this. I mean, if you want to have a pseudocode instead of this drawing, then you can have this, which is also given in the FIPS. A is the state of the input, x, y, z. If I get here, you see here x, y, z. X is in this direction, y in this direction, in z. And it says exactly what is the output bit when this is the input bit. Yeah? A is the input fully, and this is the output. Now, by this, you do it for every x between 0 and 4, y between 0 and 4, and z between 0 and w. What is a w? Is the b divided by 25. Yeah? B was the state size, and then you divide it by 25, you get the how many of these slices you have. And then this is a story about the design of the Keccak. This is a theta prime function. Why not theta? Because it was changed later to theta. And theta prime, it was the first attempt at mixing the bits, because you have the the chi function, which you can call it also as box, because it's a bijection. Yeah. I mean, if you see there's elements in symmetric cryptography, it's a substitution box, but then you need some diffusion layers. And one of the parts to implement the diffusion is that this theta prime function. And then I mean, there are some formulas for this. I mean, these plus are just XORs. I mean, it says which bits should be calculated, or how many bits should be XORed together to make the next bit. And you see some effects of this, which is not bad. It says add to each cell parity of neighboring columns. Yeah, and then you see the effect of theta prime here, which is not bad. And then it has been seen that, okay, the diffusion of theta prime is something like this. If you have a single bit change here, you apply the changes actually over this part. If you have but 2 of them, when the application of these 2 bits are flipped, then exactly the same 2 bits are also flipped at the output. Now the theta prime was not perfect. No? Diffusion of the inverse of the theta prime, you can see this is something like this. Again, from symmetric cryptography, from that perspective, this is important. And then it's tweaked, and it says, okay, let's do it like this. No? Let's do it like this, that if you have one single bit change here, then it applied actually on this slice and the neighboring slice. And then, again, diffusion of the inverse of this is much better now. Then you have those many changes to just have this guy changed. And then the steps of theta are pretty long. Yeah? Means that there are a lot of XORs for all pairs of x, z. I mean, x between 0 and 4, and z between 0 and w. Then you actually do it like this. Means that you completely ignore y, yeah, because you just, wait a second, you just calculate this as a temporary value, c, which is XOR between you see and y. Y, it doesn't matter, y was the column, means that you XOR all of the values of the column together. And then you also get this column value, you XOR them together, some of them, you get the d value for x and z. And then you apply here again, this is the input, this is the output, and then you apply the same value of the column, apply the same d on every value of the column. You know, you see that this is completely independent of y. It means that the same value is applied on every column individually. Then there is another function, which is the row function, which is the inter-slice diffusion. You see here that there is no XOR at all. I mean, this is just changing the position. I mean, the value which are here, they are just moved like here. But for different different x differently. You see this is one of them for example x equals 0. Another one for x equals 1, you have another different kind of a permutation, and then for each x you have a different form of permutation. Now this is again officially or formally defined. What are the steps of the row? Then you can actually follow this. I mean, either in software or hardware, or you run it this first, and then you find out what should be the next position of every bit for a particular design, particular W, and then you can have a lookup table for the position of the output. I mean, similar to the shift rows of the AES. Now, iota is to break the symmetry, because everything is the same. And I have to say that one function of the Keccak, this permutation function, is a sum of a couple of rounds that we will see. But then if every round or all rounds are similar to each other, then this is a problem. And then you need to actually break this symmetry. Similar to the AES, how is it done? Using the key schedule. The key schedule has a different round constant. And the round constant is different for every round. And here is the same. You have iota, which is actually a round dependent constant or round constant. And then it avoids vulnerability to slot attacks, and defective cycle structure. Then there is a round constant, which will be, again, similar to a round constant of the AES. It's just the addition, which is something is added to the state. But how to calculate this? It's a bit more complicated than what you have seen before. Then for every instance of the Keccak, then you have to think about, or you have to sit down and run this algorithm and then find out the round constant, or compute them on the fly if you have the software implementation. Another function is a P function for distributing horizontal and vertical alignment. This is again, now what you see here is just the position. Just the positioning means that there is no XOR. They are just the position of the values are different now in different slices. What you see, you see that here, for example, each of them actually is differently positioned. Now this is now officially defined, formally defined, that this is the input, and by this you make the output. This is just similar to what you see here, some kind of rotation. I mean, you rotate here over this, you rotate over this somehow, you rotate over this, and so on. Now the function or Keccak F permutation has some rounds, and every round is built like this, that you first apply theta, and then rho, and then P, and then chi and iota. And the number of rounds, how many of rounds you need to apply, is actually 12 plus 2L. And what is L? B, which was the size of the state. And then you had the F function, again, B size. And what we said is that W equals B divided by 25. For example, we had B equals 1600, and also we had B equals 200. And then W becomes here, 25 becomes 8. And how many times is like this? 64. Now, the log 2 of W is also L. Now here means that actually 3, and this is actually 6. Yeah, the number of rounds will be 12 plus 2L, and as we said, L is the log 2 of W, and W was B divided by 25. Yeah, and then this this toy version with B equals 25, we had only one slice. Now they had 12 rounds, and for Keccak 1600, you need 24 rounds. Means that these functions should run actually 24 times until we have just one instance of the F permutation. No? And F permutation was something like here. And there are different applications. One of them is, for example, that regular or salted hashing, that you have here the 0, you start with 0 state, and then you start to pad the messages. Like this, as we said, each part of the message block is just R bit, and then this, if it's F or Keccak 1600, then you need 24 clock cycles, 24 rounds of the F function. If you implement every round in a clock cycle, then you need 24 clock cycles only for this F. And the same as we said here, I mean, salted hash, if you know salted hashing, then it's similar to this. And also for MAC, or message authentication code, there are different standards. One of them is what is suggested by Keccak. I mean, you add the key here, and then you pad the message here, and then at the end you get the MAC. Of course, there are different standards. How to use, for example, hash functions to generate the MAC. But this is something which is suggested by Keccak team. I'm not sure actually this is a standard. No, there are, I think, different size and different way to do that, and then the key should be also padded and so on. Then we see one implementation of Keccak now that I have provided for you. And as you see here, there is no CMOD A7 framework. Yeah, means that it's just the Keccak. We'll see together. This is somehow parameterized, but it's not completely. And your job is to actually make it for the other parameter, one more parameter, not everything. Yeah, but this is now what you see here is for B equals 200. And there is a clock, there is a reset, and input data, which is B bits, output data also B bits, and then ready signal means that the computation is done. And then for B equals 200, we had W equals 8, yeah? 200 divided by 25, yeah? 12 plus 2L, and L was 3, yeah? For the B equals 200. And then we have together 18 clock cycles. Good. Now, everything is straightforward. You have Keccak theta, Keccak rho and phi together. There is a Keccak chi and iota together. Iota was just XORing with the round constant, and there is a control signal or control module. And is exactly similar to other designs that you have a large multiplexer at the start to select whether the input is coming or the feedback. And then there's a register which saves if reset is 1 or the computation is not done. I mean, it avoids or helps us to stop the computation when the ready is 1. And here there is a theta and rho and phi and blah, blah. Okay, what is a theta now? Here, there is also a way, I mean, I can explain you here the new constructions that you have not seen before. Means that we define a function in VHDL. Means that you can define a function just for the computation. But again, this is not something which is synthesizable. Yeah, means that you use it in a process and the synthesizer understand, okay, it will simulate for all instances and then understand what should be the design and then build a circuit which works exactly as you want. Yeah, means that this 5 times x plus y is not really implemented in hardware. Yeah, this is just calling this function during the synthesis. What is this function? We have defined an IDX, which receives x and y, both of them as an integer, and the return value is just 5 multiplied by x plus y multiplied by w. And w is something which we gave as the input or the generic. It means that during the synthesis, it's already fixed. And how this works, I have another function also, rotate to right. Rotating to right for a particular size, how many bits you want to rotate. If it's parameterized, then you can also write a function. But what I did for the rotate right, this is pretty simple. If you had x and you wanted to rotate it, for example, b bits to the right, I copied x actually 2 times. Yeah, and then here 0 to b minus 1. And from b, I took actually, if x was L bits, I took the L bits. And here is the out y, which is actually x rotated b bits. Yeah? Of course, you can draw it also differently. Then also I have this function. I would suggest you to read this function and understand how the functions work. I mean, you need to just define it, where you also define the signals and so on. And you see here, there is the return value of this. I mean, here you define the inputs. The return value doesn't have any size. I mean, it doesn't have a size of saying that how large is the size of the output. You just say it's the standard logic vector. You don't give the size. And then here, the return value here as a variable means that you define the variables which are inside the function. And one of them is this that I want to send as return. And this is a standard logic vector, and that's fine. No? You should not actually give the size of this here. Now, the theta function, there is also a loop for generate. I think we have seen this before. I have shown you this before, that you can have a loop for generate, but then it means that during the synthesis, the synthesizer will repeat this loop. For example, here 5 times with x equals 0 to x equals 4, and then actually make the circuit 5 times and then synthesize it. How it works, you see here, this is just the XOR to build this C value, which if you remember, I mean, I can show you the slide. How was the theta function? Here is the C, how to calculate this C. First, the C is calculated, and then afterwards you apply the C, XOR sum of also C, modulo something, and then put it in the D. The C here. And then you also need C to be rotated. You see C rot is actually this guy. You see he is rotated. X minus 1 modulo 5 and x plus 1 modulo 5 and z minus 1 modulo 5, yeah? And this is the part which rotates this. And this generates the columns, and now you apply this. Here. What I want to say, I mean, what is this IDX? This is actually when we have the state in a long vector, for example, b bits, and then you actually want to work with it with x and y and z. But then to turn this x, y, and z to a value, then instead of multiplied every time x multiplied by 5 plus y and then multiplied by w, everything is done in that function that you can easily use it. Otherwise, you may make a mistake in one of this multiplication by 5 plus y and then multiplication by w. And this is the theta function. I mean, there is no process or something. It's just fully combinational. It's written like this by some generate loops. And the next one is rho and phi. Here, you see here that again the idx function, the same function is used. And I have also a rotate function, which is here. I might, no, it's just okay. Wait a second, I may have made a mistake. Probably we don't need this rotate function here. Yeah, no, we need it. We need it actually, okay. And then both of them are done at the same time. You see that actually there is no XOR any other operation. This is just the positioning the values. And then they are done at the same time with rho and phi. What is important, what I also did, which you have not done before, I have used a lookup table here because I want to rotate differently for every position, based on here, phi, you see that the positions are completely different based on every value of the x. And also for phi, you see also the positions are also different based on this function that you have. Then I have defined an offset array. I mean, this is wrong. This should be offset array. Offset array. Because I have this array here. And I want to have an array of constants. I mean, you have learned before how to write a constant. Constant value, blah, blah, of type integer equals like something. Now, how can you have an array of constants? First, the array is defined, which is the 0 to 24 of which type of integer. And then you say the constant, or the name of the constant of this type of array. And then this is what you have done before. And then to give the values, you have to put the parentheses. You see the parentheses here? From here and here, you have to put them, to say what are the values of the constant in the array. And these are again to generate loops, to build this based on this rotate offset, what you see here, and the rotate function, and again changing the value of the output from rho to have it the phi applied. Then chi and iota together. For the chi, we have defined a Keccak S box. I mean, as I said, this is a kind of a substitution box. And what is this S box? It actually receives 5 bits, generates another 5 bits. And this is what you have already seen here, this guy. This inverter ANDs and XORs are exactly here. There is an AND XOR, which is defined, AND XOR together 5 times. And an XOR is one of the inputs is inverted, ANDed with another input, and the output is XOR. This is exactly what you see here. One of the input is inverted and then XORed with another input. Then you just need to instantiate this 5 times and make sure that, okay, you put the correct value at the input and output. Then this is the Keccak S box. And the application of the chi is applying this on every row individually. And then here, the application of this, W times 5 times. And then I have used another function, rho idx. You see here that also instead of applying this 5 times idx and then idy plus 1, this is exactly what you have seen before. I mean, x multiplied by 5 plus y and then multiplied by w. And the end is here the XOR with the iota round constant input. Now, what else? The control logic. The control logic is very simple. It starts if the reset is 1, it starts. Yeah, if the 0 is 1 is 0, it means that the reset is done. Then it enables counting, and also says that okay, the next state is to do the chi and iota and the next lambda, blah blah. If every name can be taken here. Yeah, and then you enable counting, and then you check whether you received the last round, and then you stop. And yeah, here you have to take care of the counter. See, for example, here it counts upwards. And what is also important, I mean, the counting just 12 plus 2w, which was 18 times, is not hard. I mean, you can have just a counter, count from 0 to 17 or to 18 to a stop, but here the round constant. The round constant is hard-coded now. It's not for w. Means that here everything is calculated beforehand, and this is a lookup table. But then if you change the variant of the Keccak, then you have to recalculate this based on the equations, formulas, and the procedure which is given in the official document. No? I mean, it's not similar to what you have seen for the AES, that you have just 1 and then multiplied by 2 and so on. Because if you want to write it down in hardware, probably it might be a bit larger than having the lookup table. But yeah, you may also implement the algorithm here for the round constant. Good, that's all. And in the simulation, but I also want to show you something new. I mean, there is no framework for the CMOD A7, but then the Keccak itself is instantiated, the permutation function. And what I do here, I just give this input, which is the test vector. And then what I want to have, I don't want to look at the output and see whether this actually looks like this or not. Yeah. Then what you have not seen before, this is something that you can actually plot or write down on the simulation panel or console. No? Means that you say assert, and this is the condition. If data out equals this, yeah. Actually, this is the other way around. I mean, this is the assert, means that it checks whether this is true or not. If it's false, then it reports, yeah, it writes actually just on the panel wrong. I mean, you can have anything here, yeah, doesn't matter. This is the text. And then you can define also severity as warning, means that if it just plots it and it passes, it goes in the next step. If you write the severity as error or failure, it stops there. You know? I mean, it doesn't continue anymore. But then the problem is of the assert, you cannot have else. Then you have to do it once for the equals, one for not equals. Yeah, I mean, keep in your mind it's the other way around. Yeah, you want to write down correct if the output is equals like this. Then you have to write assert data out not equal what you want to just write down in the panel correct. Now we can run a simulation. How it helps you, I mean, by this assert here, you see here something is written warning correct. Yeah? Then you don't need to every time look when is it done, yeah, whether the output equals what I want to have or not. Particularly if one particular output, certain output is available only in 1 or 2 clock cycles. Yeah? You see here the warning which is given here.